Hello everybody, so I'm here to mark the exam with you. I've got a green pen and I'm going to be actually answering the questions with that, and I've got a blue pen. I'm going to be making some annotations to help answer the questions. In that, you need to do the same. So first question we've got is about the pendulum. Now what you need to understand here is that when any object is lifted, so I'll write that down here. When any object is lifted, its gravitational potential energy store increases. So at point 2 the pendulum hasn't been lifted, at point 1 it has been lifted, so the gravitational potential energy store is greater here than here. Now what you also need to understand is that if it's a human lifting an object, humans get their store of chemical energy from food. So you're aware that we get our energy from food. That's a store of chemical energy. That helps us answer this first part, because it says as you lift a pendulum you transfer energy from your arm's chemical energy store. I'm writing this in green now because it's the answer, and we go from here to lift the pendulum, and that means that the pendulum has a gravitational potential energy store. So that's 1 mark, 1 mark. Let's move down a little bit. When the pendulum drops, it speeds up as energy is transferred from the pendulum's gravitational potential energy store. That's here, and then we can imagine it swinging down. Any object which is moving has a kinetic energy store, so let's make a little annotation to help us remember. Kinetic energy is stored by any moving object, including the pendulum here. So this transfers to the kinetic, let me change my pen, energy store. It wants you to pick the point when the pendulum moves the fastest. If we as we've just said, the kinetic energy store, or in fact the gravitational potential energy store, is going to be greatest here. That's transferred into the kinetic energy store as it moves down, and therefore point 2 is where the pendulum's moving fastest. It's where the kinetic energy stored in the pendulum is the greatest, so that's point 2. You can imagine that. Oh, done it in the wrong colour pen. You can imagine that in real life. If you imagine something swinging, it's always going to be fastest at the bottom of its swing. Okay. Right, so we've got a light bulb. Let's start to bug our question. I'm going to do that in blue. 600 joules, 5 minutes. Now it tells us 450 joules is useful and the rest is wasted. It wants to know how much energy is wasted by the light bulb in these 5 minutes. So what we need to understand is that energy is never created or destroyed. and that means that the energy wasted and the useful energy are going to equal the total energy. To work out the wasted energy, we can simply do (600 joules minus 450 joules), and that's obviously 150 joules. We can write it down there as well, 150 joules. Now, it wants us to identify the energy store that the wasted energy is transferred into. If you have a think about it, you wouldn't go over and just, grab a light bulb that's been on for 5 minutes, right? Why wouldn't you do that? You might get an electric shock, yeah, but it's also going to be really hot. All energy is eventually transferred to thermal energy. In this case, the thermal energy is not helpful. You don't turn a light bulb on for heat, you turn it on for light. The answer to that is thermal. Okay, there's actually a little bit of a mistake in this question. 2C, it says efficiency is the ratio of useful energy to wasted energy. It's actually the ratio of useful energy to total energy. So don't worry too much if you got the question wrong, just pay attention as I go through it. It wants you to calculate the percentage efficiency of the light bulb. So what you need to do is write down the useful energy, which we were told was 450, divided by the total energy, which we were told is 600. That's our ratio there, ratio of useful to total. If you do that, you will get 0.75. Then the last thing to do to make it a percentage is to multiply it by 100. That'll give you 75%, and we can write it down there as well in the little area. Okay, let's move on. Now, we get a lot of information in this question actually. It's just really important that you read it fully and understand what it's asking you to do, because once you've read it and understood it and had a little think, it's not really that difficult. Okay, there's an electric kettle. That's some key information. It's plugged into mains electricity and it's used to boil water. Obviously it's a kettle, right? Mains electricity is produced in a coal burning power station. Now, energy is transferred from the chemical energy store information of the power station to the thermal energy store of the water. I want you to describe how energy stores change and how the transfer takes place. Right? First thing you need to state is how the first chemical energy store changes. If we start off with all of the energy in the coal burning power station and that begins to transfer to the kettle, the chemical energy store, I'm always getting my pens mixed up here, aren't I? The chemical energy store is going to, have a think about it, it's going to decrease because we're using up some of the chemical energy, or at least transferring some of the chemical energy to another store, so that is going to decrease, right? The thermal energy store is going to, what's it going to do? Have a think about it. It's going to increase because the water is being heated up, right? We're using some of this chemical energy, transferring it into thermal energy to, boil the water in the kettle. How does it work? There's a lot of clues in the question. The transfer
due to electricity. That's your key word there. You could say electrically, electricity, anything along those lines. That's 1 mark, 2 marks, 3 marks.
Okay, next one. Oh, just a little question before we move on to question 4. All of the energy in the thermal energy store of the water is eventually transferred to, the answer is the surroundings. Now, that makes sense. If you make a cup of tea, You've boiled some water, you've mixed the tea bag in with the water surroundings, and then you just leave it on the side. In about half an hour or so it'll be completely cold, or the same temperature as the room. And that's because the thermal energy store of the surrounding of the water or the tea is being transferred to the surroundings. It's being transferred to all the molecules in the air, a little bit to the table that it's sat on, and that basically happens for any object which has a thermal energy store higher than the surroundings. Give it time and it will become the same temperature as the room it's in, and the thermal energy store is transferred to the surroundings. Okay, so we've got a bit of a calculation question next. That means we need to make sure we're bugging. A car accelerates from a set of traffic lights. The driving force on one back tyre is 3,000 newtons. Okay, I'm just going to underline this bit as well. Driving force, 3,000 newtons. Calculate how much work is done. So we're going to box that bit by the force of two back tyres. Right? I bet a lot of people miss this. It says one back tyre is 3,000, two back tyres at once. And we're also told that it moves 10 metres. Show your working, include a unit in your answer. Okay, so let's list our values. Force, again using my blue when I should be using my green. Force equals 3,000 newtons. That's for one tyre. So what do we need to do? For two, we need to multiply it by 2. Gives us 6,000 newtons. The work done, let's call that W. We don't know, we're trying to work that out, but the units are joules. You should know that. The distance, lowercase d, as well, which
you should do. This kind of stuff you just need to learn off by heart. And then you need to do work done equals force times distance. That's a simple one to substitute into here. So work done is equal to 6,000, not 3,000, multiplied by 10 equals 60,000. And don't forget your unit, joules. You need the joules for the third mark. If you get 60,000, that's 2 marks. If you just have that without anything else, then you can get 2 marks because it does tell you to show you're working. Just be reasonable. Okay. The main useful energy transfer here, well, what's the point in a car, right? The point in a car is to move, right? To take you somewhere. And we know that any object that moves, as we've said before, has a kinetic energy store. Now, cars and motor vehicles work because of the fuel that's in them, right? The petrol. Now, there is a chemical energy store in the fuel. So we'll write the chemical energy store of the fuel. If you've written petrol or something like that, that's okay. That decreases. And the kinetic energy store of the car increases. Now, you don't need to have written all of this to get your marks. If you've just written chemical energy store transfers into kinetic energy store, that is fine. But this is a more complete answer which is going to aid your understanding. Okay, one energy store that increases but is not useful. If you ever see a question like this where it wants to know about wasted energy, just write thermal energy. Yeah, the tyres are going to heat up, the road's going to heat up, parts of the engine and other things are going to heat up as well. That's not useful. We don't get a car for it to heat up unless you're using the heating inside. You get it to take you places, which is the useful energy, the kinetic energy store. Okay, we're getting there. The main energy transfer that takes place when a wind-up toy is released and starts moving. So I always find it quite helpful just to draw myself a really simple diagram when you see these quite complicated questions. 5 marks, and
it says we must include 2 energy stores, so we'll underline that, 1 method of transfer, and you must also state how the energy stores change. So already I'm thinking, right, there's probably a couple of marks available for the energy stores, 1 for the transfer, and then the other 2 marks must be because of the change. So if I'm having a think here, we've got, and I'm just going to keep it simple, I don't want to draw a detailed picture of a wind-up toy. We've got our object here, right, it's going to start off stationary, yeah, the wind-up toy doesn't move unless you wind it up, right. Then the next thing that happens is you're going to wind it up, and then we know there must be some kind of energy stored,
and then it's obviously going to start moving, right? Okay, when we see the word movement, we're thinking, right, kinetic energy. When we wind it up and these things work through springs, we're thinking elastic potential energy. So already we've got a couple of marks, right? Because we've got 2 energy stores. Yeah, kinetic energy is our last energy store, so we'll talk about that at the end of the question. The elastic potential energy store we can talk about at the start, so I'm going to switch over to my green pen because I'm going to start answering now. We'll say the elastic potential energy store increases because you're winding it up, right? Increasing the store within the toy. Now, how do you actually wind a toy up? Well, you've actually got to take your hand and wind it up, right? So we would say that this happens due to a force. So we'll say the elastic potential energy store increases, transferred by a force, yeah, or you could say transferred by someone applying a force. Now, when you let the toy go, it then starts to decrease its elastic potential energy store, which is transferred into the kinetic energy store, and then you get your last mark for saying that a kinetic energy store increases. Now, you can get 5 marks. I think that's probably the easiest way to do it. If you've mentioned a person and their chemical energy store transferring into an elastic potential energy store by a force, then you can give yourself a couple of marks, but you do need to mention the kinetic energy store, which increases, to get full marks. Okay. Right, last question here. It's quite a complicated one, requires quite a lot of working out, so we need to make sure we're bugging because it's a calculating question. We've got a motorbike of mass 400 kilograms. He applies the brakes and reduces the speed from 20 meters per second to 4 meters per second. So there's a deceleration taking place. The kinetic energy store can be calculated using this equation, which is half times mass times velocity squared. He wants to calculate the change in kinetic energy, or the kinetic energy store, as they slow down from 20 to 4 meters per second. Again, we've got to show our working and include a unit. Now, let's start listing our values. Because it wants a change in kinetic energy store, we're going to have to calculate the kinetic energy store at 20 meters per second and the kinetic energy store at 4 meters per second, and then find the difference, right? The change between the two. So I'm going to do two separate calculations here. I'm going to work out the kinetic energy at 20. I don't know that yet, and that would be in joules. And I'm going to work the kinetic energy out at 4 meters per second. Don't know that yet. But the unit is joules. We do know the velocities. We said that this was 20 meters per second, and we said that this was 4 meters per second. The mass of the bike is the same in each case, 400 kilograms. 400 kilograms. I don't have a huge amount of space here. I might be able to just squeeze it on. We can start to substitute this into the equation. So kinetic energy equals a half times 400 times 20 squared. So you need to do the 20 squared first, then multiply it by 400, then multiply it by a half. If you do that, you're going to get, I worked it out earlier, 80,000 joules, right? It makes sense to do this. 20 squared is 4,000, by the way, so make sure you've got that calculation first, then you do the 400 times the half to give you 80,000 joules. Do the same thing over here, but obviously with a different velocity. KE equals half times 400 times 4 squared. 4 squared is 16. Then you times that by the 400 and by the half. That gives you 3,200 joules. Now the last thing you've got to do, so if you got to this stage, you'd get yourself 3 marks, right? Because you've calculated basically everything you need, you just need to get the final answer. So if you do 80,000 minus 3,200, that gives you the change in kinetic energy. That was the kinetic energy when he was travelling along at 20 meters per second. This was the kinetic energy when he slowed down to 4 meters per second. That gives you 76,000 800 joules. That's your final answer. You need to include a unit, otherwise you only get 3 marks. If you've got that, 6,800 joules, that's 4 marks. Okay, how much work is done by the motorbike by the braking force? Work done is the same as the change in the kinetic energy. So the answer to this is 76,800 joules, right? No energy is created or destroyed. The amount of work done by a force over a distance is the same as the kinetic energy change in the bike. And then last one here requires a bit of knowledge of Newton's second law of motion, which is simplified as F equals ma, force equals mass times acceleration. A deceleration is the same as an acceleration, only that here you're getting slower and with an acceleration you're getting faster, but the units are the same and you can use it in this equation. That's 3 meters per second. We've got a mass from before which was 400 kilograms, so we can use this equation. We'll list the values first. It wants you to work out the braking force, right? So we would box that. We don't know what that is for now. We do know the mass is 400 kilograms. We do know the acceleration, which we're just given, or the deceleration is fine, 3 meters per second squared. Our equation F equals m times a, so F equals 400 times 3. That's quite simple, isn't it? 12,000 newtons now, because it's a force. 12,000 newtons, 3 marks for that, 2 marks if you didn't have your unit, 1 mark if you got 400 times 3 but didn't get any further than that. Okay, so actually got 32 marks this one, but it was quite a quick exam to go through. Okay, if you have any more questions you can come see me next Wednesday after school is the best time, or find me in the yard, or speak to your science teacher at an appropriate time. Okay, thank you.